Hey friends, how are you? Let's have a look at problem 2359 together, a newly appeared problem. So for this problem, we are required to find closest nodes to given two nodes. So this is a graph problem, and in this video, we're going to share a classic method based on breadth first search. So here the requirement is the following. So we are going to return the index of the node that can be reached from both the two sources, node 1 and node 2, such that the maximum between the distance from node 1 to that node and from node 2 to that node is minimized. So actually the last sentence is also important. So if there are multiple answers, we should return the node with the smallest index. Actually, in my first several try, so I forgot this condition. So the logic is right, but the return is not right. So there's one case missed. So notice that the edges may contain circles. So here is an example. In this example, the return is node 2. And in this example, the node is node 2. It's one of the two sources, actually. So the constraints are mainly on the number of nodes. So the number of nodes can be up to 10 to the power 5. So it's a decent large number. And this one, edges I, does not equal to I. And the last one, node 1 and node 2, the two sources are in range. So this is natural. So with that said, let's look at the solution here. We are going to present. So the solution is a breadth first search. The reason is that this is basically a shortest path problem. So the procedure is as follows. We first use breadth first search to get the reachable nodes from the source, and then record the corresponding shortest distance. I will say distances. And then we use that to find commonly reachable nodes. And then we can prepare the return. So this prepare the return is not that trivial. So we should notice this sentence here. Here is the caution again. So if there are multiple answers, we should return the node with the smallest index. This is the example that my solution didn't pass at the very beginning. So the node is 5 and node 2 is 6. We should return 1, not 4, because 1 is less than 4. But for this, both of the two nodes, the maximal of the distance to the from the corresponding sources are 3. So with that said, I guess we are ready to share the code and analyze the code. So so this import two things. One is deck. We are going to use it as a queue. So this is not absolutely necessary. Similarly here, the default dictionary. So we're going to use it to build a graph. These two imports are basically for convenience. So with that said, basically we're going to split the solution into 3 parts to make the logic clear. First step, we're going to build the graph. So in the problem, actually the graph representation is given by a list. So we're going to use the node adjacency list representation. So actually we are going to, for each of the nodes, we're going to store a set of nodes. If the node have a direct edge with the key. So with that said, let's do this job. So before we do this, maybe just notice example 2, right? So let's do a special case check. If node 1 equals node 2. So in this case, let's just return node 1. So this is not absolutely necessary following the general logic, but let's treat it maybe. So let's build the graph. So the graph, I'll call it graph. It's default dict. I'm going to use the set as container. And then we're going to iterate through the edges. So then we're going to check if v is not equal to -1. It means that from in node I, we can reach this node v, right? So what we're going to do is that we add this node to the adjacency list of node I. So this way we finished building the graph. And next, we are going to do breadth first search hyperfunction. So this is going to use this queue container. So for this, let me call this function breadth first search, and we accept a node as argument. So we are going to store the reachable nodes and the corresponding shortest distance from this source. So let's initialize this queue by dec and v. And then we are going to do the iteration. So first, let's use a dictionary to both monitoring the iteration or traversal, also recording the corresponding distance. So this is a while loop, while queue. So we first get the node and the distance. So the distance is the queue pop left. So then, because we're visited this node, we're going to add this node to this dictionary, meaning that we visited this node and we record the corresponding distance. So that's the role played by this dictionary visited. And next, we are going to look at the neighbors for this node. So we are going for node in graph node. So here is a neighbor in graph node. Then we're going to check if neighbor not in visited, meaning that in the expansion of the breadth first search, we haven't meet this neighbor yet. What we're going to do is that we enqueue this neighbor to the queue. So the distance should be incremented by 1. So with that said, I guess this is the end of the breadth first search function. So we're going to return the visited. So that's it. We prepared our tool. Next, we call the breadth first search function and prepare the return. So this is the place where I didn't prepare prepare or return the result, the desired result. So let's do it carefully. So let's call S1 and S2 is the BFS nodes 1 and BFS nodes 2, right? So these two dictionaries stores the corresponding reachable nodes from the two sources and the corresponding shortest distance. Then we're going to let's first find the common reachable nodes. So it's basically a set operation. So S1 case, the intersection with set S2 case. Oh, that's it. So now let's iterate. So one thing is that if not S, so we're going to return -1. So this is the by requirement from the problem. Next, we're going to prepare the result. Let's first set result equals -1, and we because we want to compare the minimized maximum distance, so we're going to let's see, we're going to use a distance as a reference. Let's call it float. That's infinity, right? And then we're going to do the iteration for node in the common reachable node set S. So we're going to compare the maximum distance. So this is maximum of S1 node and S2 node. So we want this temp variable to be as small as possible. So then we're going to consider if temp is less than D, then we're going to reset the result to be the current node, and we're going to reset the distance to be temp. So here we cannot return yet, so we need to consider another case. That is, if there are multiple answers, we should return the node with smallest index. So this corresponds to temp. If temp equals D, then we do not reset the result state, but we need to reset the return. So the result should be, so let's see, if node is less than the previous result, or the node index, so we're going to set the result to be the node. and then actually we can return the result. So let's see. Yeah, that's about it for this format of solution. Let's do a special case check. So unknown packing. So pop left. Let's see. Q pop left. Q. So here, let's see. We forgot to make it. So we want to store the nodes and the corresponding distance. So at the very beginning, this should be 0 from the source. Let's do the check again. Yeah, it passes a special case. Now let's do the generic case check. Yeah, it passes the generic case. You can see here in my first several tries, so I didn't write this else if condition because I ignored this this part here. So with that said, I guess we can give a quick summary of this solution. So here we are using breadth first search because it's essentially a shortest distance problem. So we split the solution into 3 parts. The first part is actually building a graph, so for convenience of traversal. And the second step is to write a breadth first search hyperfunction to make the solution modularized. So in the queue of this breadth first search container, so we use a tuple. The tuple stores the nodes and the corresponding distance from the source. And thirdly, we get the commonly reachable nodes set and then prepare the return. So here is a caution when we prepare the return. We need to consider or be aware of the case that some nodes yield the same maximal distance, but we need to return the smaller index node. So with that said, I guess that's about it for this solution. Thank you very much.